Welcome to the Deep Dive. We're the place where we cut through the noise, unpack complex topics, and really try to unearth those fascinating nuggets of knowledge you can use. Today, we're plunging into an absolutely critical area for, well, pretty much any business handling online transactions. We're talking about ensuring PCI-DSS compliant serverless payments, specifically on Google Cloud Platform, and using some truly cutting-edge security tools to do it. So, for you, our listener, maybe you're prepping for a big meeting, or perhaps you're just really curious about how companies are securely handling sensitive payment data in the cloud these days. Our mission today is to slice through that complexity. We're going to explore how a multi-layered security architecture, leveraging technologies like confidential VMs, cloud external key manager, and binary authorization doesn't just meet strict compliance rules, but actually provides an unprecedented level of control and security. It's really about getting to the heart of what makes these systems not just compliant, but profoundly, fundamentally secure. Let's unpack this. Okay, so when we talk about processing payments, especially in a cloud environment like GCP, what's the fundamental security challenge we're really trying to solve here? Because it goes beyond just encrypting data when it's sitting still on a disk or, when it's moving across the network, doesn't it?
Absolutely. You've hit on the core issue there. It's this concept of data in use.
Hmm.
Most people get encrypting data at data sitting on a disk or data in transit as it moves over the network. That's fairly standard stuff. But what about when that data is being actively processed by a computer? When it's sitting there in memory, being computed on, that's actually where it can be quite vulnerable.
Right, when the computer is actually using the information.
Exactly. And this is where we see risks like memory scraping. That's essentially malicious software trying to sort of uh, grab sensitive data directly from a server's active memory.
Yep.
And maybe even more concerning are hypervisor-level attacks. That's where an attacker might try to compromise the underlying system software that runs Google's cloud infrastructure itself, potentially getting access to the virtual machines it hosts.
Wow, okay, so attacking the foundation itself.
Precisely. These are the kinds of blind spots that, traditional encryption methods alone don't really cover effectively. And this specific challenge, it really demands a truly multi-layered security architecture.
Mm.
You need defense in depth. And that's exactly what we're seeing with this approach, this combination of three powerful pillars: confidential VMs, cloud external key manager, and binary authorization. Each layer tackles a different critical aspect of security and compliance, especially for sensitive payment data, and they really work together.
Okay, that sounds incredibly sophisticated and maybe a bit abstract when you just list the names like that. Confidential VMs, EKM, binary authorization. But I know we can make this crystal clear. I actually heard a great analogy for understanding these three components, thinking of it like a really, really secure package delivery service. How does that analogy help us visualize how these distinct pieces fit together, to protect something as sensitive as payment info?
Oh, that's a perfect analogy, actually. It really helps clarify their individual roles and how they contribute to the overall security. Okay, so first let's talk about confidential VMs. In our analogy, you can imagine these as the armored vans. The key point here is once your package, your sensitive payment data is inside this van, not even the courier, right? Which represents Google Cloud's underlying infrastructure in this case.
Mm-hmm.
Not even they can peek inside that package while it's in transit or being processed. The data inside is encrypted even during computation.
Even while it's being worked on.
Yes. And this significantly reduces the risk of that memory scraping we talked about, and it also protects against those potential hypervisor-level attacks.
Yeah.
It's like having this secure, tamper-proof buttle where your most sensitive operations are totally isolated.
So if I'm getting this right, it means even Google's own engineers, the people managing the cloud infrastructure, theoretically couldn't see your data if they tried to access the virtual machine's memory. That feels like a fundamental shift in trust, doesn't it?
Precisely. It fundamentally redefines the security boundary. Traditionally, you placed a lot of trust in the cloud provider for the infrastructure security. With confidential VMs, you're basically extending your encryption shield right into the CPU itself. So even if the underlying cloud infrastructure were somehow compromised, your data should remain encrypted during processing. That's a huge leap.
Okay, that's the armored van. What's next in the analogy?
Right. Next up is the Cloud External Key Manager, or EKM. Now think of this as having the keys to open that package kept securely in your own personal, impenetrable vault. GCP, the courier, can deliver the package, they can run the armored van, but they can never unlock it themselves.
Why is that separation so critical?
It's crucial because all the encryption and decryption operations for your payment data require real-time approval. It goes over a secure channel directly from your external hardware security module that's a dedicated physical crypto device, or your key management system. So this means you, the customer, retain ultimate custody and control over your encryption keys. They never reside within Google's infrastructure.
So wait, you're saying that I, as the customer, effectively hold the ultimate kill switch for my own data's encryption. If I suspect something's wrong, or for a compliance reason, I can just cut off access to the keys.
Exactly. That's the power. It's an unparalleled level of control. Yeah. And it's absolutely vital for meeting those really strict compliance requirements, like PCI-DSS or data sovereignty rules in different countries.
Right, data residency and all that.
And crucially, for breach mitigation, you can instantly revoke access to your keys if you detect a threat. It fundamentally shifts the trust model, giving you the final say on your data's accessibility.
Okay, armored van, keys in my vault. What's the third piece?
And finally, we have binary authorization. Picture this as the critical checkpoint where, before any package even gets loaded into that armored van, it needs to have your specific authorized seal stamped on it. Only packages with this precise signed seal are allowed onto the van for delivery. Any fake packages, tampered ones, unauthorized ones, they simply never even leave the loading dock.
So translating that to the tech.
Right. In the technical sense, this strictly admits only signed, tested, and approved container images. That's your application code and all its dependencies into your production environment.
So this isn't just about security. It sounds like it enforces extreme operational discipline, too. It means what runs in production is exactly what you intended and vetted every single time.
That's a perfect way to put it. It feels less like just deploying software and more like a controlled, audited process. It effectively eliminates the risk of unverified or tampered code ever running, which aligns perfectly with those strict PCI software integrity mandates. Now, this does require a robust CI/CD pipeline, continuous integration, continuous delivery, to handle the artifact signing automatically. That's the process of building, testing, and deploying your software.
That's a fantastic way to visualize how these distinct pieces work together. The armored van, the external keys, the authorized seal. So what does this all mean when you actually put it together in a real system? How does the architecture look, and what are the specific roles these play for hitting that PCI-DSS compliance target? It feels like more than just individual tools, but an integrated system.
Absolutely. It's about how they fit into a coherent, compliant flow. It's definitely an orchestrated system. Let's break down their specific PCI-DSS roles within that architecture. So confidential VMs, their main job is providing that robust data in-use encryption and strong process isolation. All your really critical payment handling code, the stuff actually touching cardholder data, runs entirely inside these protected VMs.
Got it. Isolated and encrypted during use.
Then, Cloud EKM. It's solely responsible for that external crypto key storage and enforcing how those keys are used. It's the mechanism ensuring your payment data is encrypted. But crucially, the keys always remain external to Google's infrastructure, under your direct control.
The keys stay with you.
Exactly. And binary authorization, that provides the essential software supply chain control and ensures container integrity. It's the gatekeeper, right? Making sure only containers signed and attested by your approved processes get deployed. It blocks any untrusted or modified code.
Preventing rogue code is huge.
Definitely. Now, for serverless orchestration, you might use services like GKE Autopilot, which is a managed Kubernetes service, or Cloud Functions. These are often used for the initial entry point and coordinating requests. But importantly, they are specifically not used for the direct payment operations or handling the sensitive data itself. This emphasizes isolation and minimizes the infrastructure you directly manage, which enhances accountability and shrinks the attack surface.
Okay, so the sensitive stuff stays in the specialized secure zones.
Correct. And then, of course, there are the crucial supporting elements that tie it all together. You absolutely need VPC Service Controls for network segmentation. Think of them as creating secure perimeters around your sensitive workloads, isolating them. You need GCP's IAM identity and access management applied rigorously, enforcing the principle of least privilege. Users and services only get the permissions they absolutely need, nothing more.
Least privilege, always key.
Always. And finally, Cloud Audit Logs. These provide comprehensive, immutable records of all activities, which is critical for compliance reporting and any incident response scenario.
It's clear it's not just one thing, but multiple layers working tightly together. Okay, let's make this really concrete. Can we walk through a real-world example? How would an actual payment API request flow through this whole secure architecture?
Absolutely. Let's trace the path. Picture this. A payment API request comes in, maybe from a customer's web browser or their mobile app. It first hits something like a GCP Cloud function or an API gateway. Now, crucially, No sensitive payment data like the full credit card number is kept or processed at this initial entry point. It just acts as a secure front door, routing the request.
Okay, so the force-stop is just a router, basically. It doesn't hold the sensitive stuff itself.
Exactly. It's designed to be a non-sensitive entry point. The actual payment processing is then securely handed off to a workload running on a confidential VM. This could be a custom compute engine instance set up for confidential computing, or maybe a node pool within GKE Autopilot configured to use confidential nodes. And this entire processing environment is further wrapped in VPC Service Controls, establishing that defined protected network perimeter, isolating it.
So it gets handed off into the secure zone.
Right. Now, any sensitive data handled within this environment, say the credit card number being tokenized or encrypted, is encrypted both when stored at rest and when moving in transit. And here's the critical part. This encryption uses a key that is managed by your cloud EKM provider, maybe Fortanix or Thales, for example. The key itself never actually touches Google's infrastructure or memory.
And every single access to decrypt using that key is logged, tightly controlled. And you, the customer, can even revoke that access externally at any time. That sounds incredibly powerful.
It absolutely is. That's the maximum control point. Then think about updates. When new versions of your payment processing code are deployed, the deployment of all those containers is strictly governed by binary authorization. This means any new code, any new container image, it must pass signature attestation. Basically, it needs to be cryptographically signed by an approved authority in your pipeline before it's allowed to run in production. This stops unauthorized or potentially tampered code cold.
Preventing bad deployments automatically. And finally, the whole system includes regular compliance validation. You'd use built-in PCI audit tools and automated controls to ensure you're continuously adhering to the latest PCI-DSS mandates and preventing any configuration drift over time.
This architecture sounds incredibly robust. It definitely offers significant peace of mind. But, as with any powerful solution, there are always trade-offs, right? And maybe potential gotchas to watch out for. What are some of those practical considerations? Things businesses really need to factor in when they're looking at adopting such a sophisticated setup.
You're absolutely right to ask. It's not just about flipping switches. It's about understanding the operational nuances and implications. There are always considerations, and it's important to get them right for a successful deployment. All right, let's start with the trade-offs you'll likely encounter. With Cloud EKM, you are introducing a dependency on an external service for your keys. This naturally means you'll see a tiny bit of extra latency, usually minimal, but it's there because there's that external communication for every crypto operation.
A slight speed bump for massive control. Pretty much. That slight latency is generally considered a very small price to pay for the drastic improvement you gain in key custody and your overall regulatory posture. You literally hold the keys, not the cloud provider. That's huge for compliance. Then, confidential VMs. They also have some considerations. They might slightly restrict the types of VMs you can use. You might not have the full range of machine types available compared to standard VMs. And yes, they can incur a higher cost because of the specialized hardware and security features involved.
Okay, so maybe fewer choices and a bit more expensive.
Potentially. But the flip side is they provide that profound defense-in-depth capability, protecting data even during active computation, which simply isn't feasible with older VM approaches.
And what about binary authorization? You mentioned it needs a really solid CI/CD pipeline. So for companies whose development practices might not be quite there yet, this could be a significant upfront hurdle, couldn't it?
It definitely requires an upfront investment, both in tooling and in process discipline. Binary authorization mandates a very robust, mature CI/CD pipeline to handle that artifact signing reliably. But I'd argue it's an absolutely essential safeguard.
Yeah.
It prevents accidental deployments. It prevents rogue code. It ensures only trusted code runs. It's a foundational discipline that actually pays dividends well beyond just security. It improves reliability, too.
Makes sense. Build it right from the start.
Right.
Okay, what about the gotchas, the things that can trip you up in practice?
Right, the crucial troubleshooting and compliance gotchas.
Yeah.
What can actually go wrong, and how do we proactively prevent it?
Yeah.
This is vital for long-term success. A major one is key control loss. If your external KMS, the system holding your keys, becomes unavailable, maybe there's a network outage between GCP and your KMS, or an issue with the provider itself, your payment operations can immediately grind to a halt because the system can't decrypt the data it needs. So you absolutely need to ensure high availability and really robust monitoring on those KMS endpoints. Treat them like mission-critical infrastructure, because they are.
High availability for the key manager is non-negotiable then.
Absolutely. Then there's VM type drift. This is subtle but dangerous. It's where, maybe accidentally through a misconfiguration, a standard non-confidential VM gets deployed into an environment that's supposed to be running only confidential VMs. This seemingly small error can completely break your compliance posture for that workload. So it's crucial to use organizational policy constraints within GCP to enforce the use of confidential VMs and also have automated post-deployment checks to validate this.
Lock it down the policy and double check. Got it.
Another critical point is a potential binary authorization bypass. What if your policies become stale? Or maybe there are failures in your signature workflows in the CI/CD pipeline. This could either block legitimate, needed deployments, causing operational headaches, or, far worse, it could inadvertently let untrusted or unsigned code slip through into production.
Yikes. So the gatekeeper needs careful maintenance.
Exactly. Consistent integration with your CI/CD gates, automated checks, and continuous monitoring of the attestation logs are key to ensuring this protective layer is always active and working correctly. And finally, never forget the foundational elements. IAM, logging, and segmentation are not optional nice-to-haves. They are absolutely non-negotiable. Implementing strict least privilege IAM and rigorously using VPC service controls are paramount. Overlapping permissions, overly broad access, or unintended network paths can create serious security gaps that undermine everything else, putting your entire compliance scope at significant risk.
So even with the fancy tech, the basics still matter hugely.
They're the bedrock. When implemented correctly, though, and with careful attention to all these details, every single element, the confidential VMs, the external key management, the binary authorization, they provide a really strong interlocking defense against evolving cyber threats.
Yeah.
And importantly, this whole architecture directly satisfies explicit requirements in PCI-DSS 4.0 regarding cloud infrastructure security, going beyond just ticking boxes. This holistic approach really minimizes your cardholder data exposure while maximizing your regulatory confidence and maintaining operational agility.
Wow, what an insightful deep dive. It's abundantly clear that building these PCI-DSS compliant serverless payment systems in the cloud, well, it isn't just about checking off requirements on a list. It's about creating truly resilient, genuinely multi-layered security. We've seen how confidential VMs protect data even while it's being processed.
The data in-use protection, yeah.
How Cloud EKM gives you that ultimate external control over your encryption keys.
Your keys, your control.
And how binary authorization locks down your software supply chain from the code check-in right through to production deployment.
Precisely. This whole approach, it's about building trust and control directly into the fabric of your cloud operations. It ensures you not only meet those tough compliance demands, but also genuinely elevate your security posture against, increasingly sophisticated threats out there. So it's really a proactive stance on security, not just reactive.
So thinking about this, what does it all mean for you, our listener? If you really consider the power of having that external control over your encryption keys, the ability to just revoke access at any moment, how does that fundamentally shift the whole paradigm of trust when you're operating in the cloud? It's a powerful thought to mull over, isn't it? Especially in today's world. That's all for this topic. Stay tuned for the next deep dive into essential DevOps and cloud engineering insights.